Before going into more examples, let's go over this theorem associated with the function representation of a power series. Now we already did that within the radius of convergence, power series can be considered as a function, right? And this new theorem says that this function is differentiable as well as integrable, right? So we can differentiate this function as well as we can integrate this function, and within the interval of convergence, and then accordingly the terms of the series will change. See, if we let's say if we just differentiate this general term, you will get NCN x minus a n to the power 1, which is this one, right? Remember, these are just constant, and this is the only variable, right? And also there's one more thing that you should add to this theorem. When you are doing these differentiations and the integrations, the radius of convergence of the resulting series will be the same, right? So the radius will not change when you differentiate or integrate, right? Now, to see the actual reason for those results, you will have to go for the proof of this theorem, and we are not going to discuss those proofs, right? So we just directly use the result or the conclusion of the theorem only, okay? And let's try to apply this theorem in a problem, right? Now consider this one. Find the power series representation of 1 divided by 1 minus x whole thing squared. And now for this one, we already saw the power series of this function, which is equal to sigma x to the power n, right? Starting from 0, and if you just expand the terms, it will be like this, right? And how do we relate this function to this one? Now, you should understand that you cannot just rearrange this term as we did before in order to get this one, right? Because here you have a squared term outside the bracket, so there is no way of rearranging this thing to get this one, right? So simply what we can do is we can just observe the derivative of this original function. So if you differentiate this one, you can immediately see that you will get 1 minus x whole thing squared, right? And then from this theorem, we can say that when you have a function like this and when you get the derivative, you can get the derivative term by term. See here, this is a constant, so the derivative, by taking the derivative, this will vanish, and here you have only a x term, so you have c1, and here you have 2c2, this term, and the power is reduced, and likewise you can differentiate it term by term, right? So now if we are going to differentiate these terms, then it will be, this is 0 and this will be 1, this will be here it should be 2, it will be 2x, and the next term will be 3x squared, and likewise this term will be nx n minus 1, and likewise it goes, right? So the power series representation will be n times x n minus 1, starting from the same number and goes up to infinity, right? And well, actually now this is a very big mistake, okay? Now here you can see, if you start from the same number as 0, and if you just plug in 0, what you will get is something like this, 0 times 1 over x, right? Because here you will get x to the power minus 1, right? So all together it will become 0, right? Now actually it's not a mistake, but you will be writing down an unwanted term here, right? Because the first index will represent 0, right? And that will not make any harm, but still it is not that necessary to start from 0. So what you can do is you can even start from 1 and you can write the same general term. Now this is not the index shift, okay? As I explained before, this is not an index shift, right? Now see, although the starting index is the same, all is different, all the other terms is the same, right? So here what happened was we just excluded the indexing associated with this starting term because it's 0, right? So adding 0 does not make any difference to the sum, right? So that's why we started at 1, okay? And if you need to do some index shifting because of this x to the power n minus 1 term, what you can do is, here in order to get x to the power n, you have to add 1. So if you add 1, you have to do it for this term as well. And if you are adding 1, you have to subtract it from the running index, right? Now see, this is starting from 0 and this is also starting from 0, but those two series have a different representation, right? If you start from 0 in this representation, you will be writing an unwanted 0 at the beginning. But once you get rid of this unwanted term and write it from as the starting index as 1 and then do an index shift. Now this is an index shift, but this is not, right? This is just excluding the first term and this is an index shift. So once you do this index shift, you will be starting from this term onwards, right? And see, in this representation also they have written down the starting index as 1. That means they have represented this one as the result, right? Now we have done several things here within this problem, right? The first and the most important thing is to know that the function representation of this power series can be differentiated, right? So to obtain the function representation or the power series representation of this function, we differentiated a known power series representation, because when you differentiate, you will get this one, and differentiating this one means differentiating the power series term by term. So you will end up with this one, and if you want to do some nice rearrangements, you can go up to this stage. So ultimately what you will have is this function 1 minus x whole thing squared can be written as n equals 0, infinity, n plus 1, x to the power n. And remember I said when you differentiate, you will not change the radius of convergence. So the radius of convergence will still be the same for this one as well. The radius will be equal to 1 because here also the radius was equal to 1 for this result. But there's another thing, right? Although the radius is the same, right? Although the radius is the same, we cannot guarantee that the new differentiated power series will also have the same interval, because now interval, when you say the interval, you can have open brackets and closed brackets as well, right? So sometimes upon differentiation and upon integration, this open or the closed nature of the interval will change, but the radius will be the same. But the thing is, this endpoints might change when you are, change in the sense they might be included or they might be excluded when you are differentiating a function and obtaining a new power series. So although the radius is the same, we cannot directly write down the interval of convergence of the new power series that you obtained. So for instance, in this example, although we know that the interval is strictly less than 1, that is this one, we cannot directly say that this function will also have the same interval. We will have to do some more calculations to figure out whether this one also includes the same endpoints, right? Because now sometimes even if in the original problem, if the power series representation does not include the endpoints, when you are doing some integrations and stuff like that, it might include the endpoints, and when you are doing differentiations, it might exclude the endpoints, right? So therefore, if you need to find the exact interval, you will have to manually substitute these endpoints once again and see whether the series converges or not, right? So remember that also. The radius is the same, but the interval may not. You will have to once again substitute the endpoints and check for the convergence of the newly obtained power series, right? So we did several important things here in this problem, right? The first one is, in order to obtain a new function, you can differentiate an old one, and when you are differentiating, you can do it term by term, and when you do that, you will obtain a new series, and the radii of the new series and the previous one is the same, but the interval might or might not include the same endpoints as it was in the previous case, right? Okay,